Swayam Prabha. Digital India. Educated India.
I'll just give you some glimpses here for generalizing some part this Lagrange formulation for electrical domain also. So this is the way kinetic energy and potential energies are defined in the electrical domain. So if you use this and for a circuit and do independently for the circuit, you'll get this your circuit expressions, whatever expressions you get in Kirchhoff's laws. Okay, but the difficult part is when you have this electromechanical coupling between the two domains, as we saw in the motor model, then things are little different. Okay, so then you see here when we talk of this inductance here, Li square term, it's only the self inductance we usually consider. Okay, when we are used to consider in the self inductance only, but when we talk of our motor, it will not only have a self inductance. In fact, the self inductance part we say di by dt term, LDI by dt term, many times we ignore that term. Okay, so the main important term in that case is going to be your coupling or back EMF giving term. Okay, so what is the term that will give you back EMF based on so that is a mutual inductance kind of a term that we need to consider, and how it is to be considered we'll discuss separately when we talk of a little bit more about the actuators and motors and things like that. Okay, so we'll not get into that, but you can give a thought to that based on our expressions for back EMF, how this mutual inductance can be considered in the kinetic energy, so that finally when I derive Lagrange formulation, that time I get appropriate expression for equations of dynamics, which is matching our Newton's formulation dynamics. Okay, so that is so one can kind of see this application that opens up if you use these kind of expressions, that opens up your Lagrange formulation application to these electrical or electromechanical domain systems as well. Okay, so we'll consider only this kind of a inductance part later, where we have to understand some more fundamentals about the electromechanical parts before we delve into these. So you need to revise some of your electromagnetics, okay, the magnetic circuits and things, fundamentals of that sort, to kind of get to really how do we consider these in different kind of cases. Okay, so we'll do that later. So now, we'll close this today's part by defining these two problems. Okay, one is called regulation problem in control. So these are the definitions for a future kind of control discussions that we'll do pretty soon now. Okay, so these regulation problems are the problems where you are given this starting point and the end point, okay, final point. So PS and P final are given. Okay, so now I'm showing it with the example of this 2 hour manipulator, but in general this can be for 1 hour also. Okay, for theta it is given as theta 1 initial and theta 1 final. Okay, it can be as simple as that. Okay, so you are given these 2 points in terms of the vector state of degrees of freedom. Okay, so it can be also the general, what you say, not just generalized quantity, but their derivatives also. You can be given a full state of system at initial point and full state at the final point, and then you are required to go from like initial state to the final state. So we typically consider for these manipulator kind of systems that initially it is starting at zero velocity from the starting point, and like it ends with the zero velocity. So typically the velocities of start and end points are zero. So that may give you the generalized coordinate velocities also to start and end to be zero. So you can see that this problem does not give you any information how do you want to move from here to here, okay? Or in other words, the time expression for these thetas to go from here to here, okay, the desired time, like I don't care like whether theta 2 in between is one value or the other value, okay, it can be any taking any value in between, but I want like the finally the expression should go, I mean the value should match, okay. Okay, so finally when it goes here, like the point P should fall on the PF, okay. So we are not bothered about this path to go from here to here, okay. When I say path, it becomes like a time trajectory for theta 2. So we are not bothered about like what trajectory of time we follow for theta 2 and theta 1 to go from this place to this place, okay. So that those kind of problems are termed as the regulation problems, okay. We are just interested in the initial position and final position, that's it, okay. So one can now see to go from here to here, like we just evaluate, okay, at this position what are the theta 1 theta 2, and when it goes at this position what are the theta 1 theta 2, and between now this, so say this is theta 1 in S and theta 1 F, and then like we have similarly theta 2 S and theta 2 F, and then we say, okay, for going from there to there I just need to kind of drive my theta 1 from theta 1 S to theta 1 F, and theta 2 from theta 2 S to theta 2 F, and my job is done, okay. I then like I say, okay, I'll first move theta 1 to that position, theta 1 F position, and then after that I move theta 2 to there. Who cares, I mean you can move them together, you can move them one after other or whatever, but you can take it to the final. So that is what is a regulation problem. So you can typically, they'll, for saving time, you'll move them together, like to start both the motors simultaneously, and then you'll reach the final point. But you are not bothered like what is the path it takes to go from here to here, okay. So so you have found, like that's what I was talking about here, you are finding these initial and final paths for the initial and final values for the generalized coordinates, and command your motors to go either simultaneously or one after other or whatever ways to go from starting to the final point. Okay, so in now this like how do you kind of this command your motors? So this is like topic of further discussion for control. So we'll see how we can control like the okay. But the regulation problem is when you want to go from one position to the other final position, or one state of generalized coordinates to other state of generalized coordinates without bothering what are the in between states. Okay, so that is our regulation problem. Okay, so we'll discuss this further when we start talking about control very soon. And then other kind of a problem that we need to understand is a tracking problem. Okay, so in tracking case, you actually want that, okay, my point P should go from this position to this position along say circular path or along a straight line, something like that. If we give, then what it amounts to defining the desired values of theta 1 and theta 2 is they should be at exactly some place in the along the path in time. Okay, so don't confuse, like if you have single link manipulator, what is the tracking problem there? It's a path is always going to be circular, so how can I define tracking problem? No, it's not that. It's like the values of theta which should be dependent upon the time in between. Okay, so I want to go from this point to, say for example, for single link, forget about this link, if I want to move from this point to say some other point on the circular path, there also I can move like slowly there or fast there, or say starting acceleration and then slowing down and go there. Like that I can have many different time trajectories for going from theta 1s to theta 1f only for single link manipulator. Okay, so that also is a valid tracking problem. Okay, although I am moving on the circular path only because there is only possibility for this single link manipulator. When you talk of two link manipulator, it's little easier to understand because there are multiple paths that can be possible, which you can see. Okay, so see what we are seeing here is like in a space kind of a variation of the path, but time variation of the path is not seen when you kind of look at this to our kind of a manipulator case, or one single link manipulator case, I would say. Okay, so now for doing this, you can have multiple paths possible. So say, let's say I am defining like this path along which I want to go. So not circular path, but I want to go along by a straight line kind of a path. Now the moment I say that, then I have to define at every point on this path, then theta 1 and theta 2 gets defined. Okay, they'll have some kind of a specific value only. Okay, so and then we should have that this theta 2 at this point of time, theta 1 should be this and theta 2 should be this for my point to be on the path. Okay, that kind of a definitions would come. So we would in general get a definition for theta 2 in terms of time and theta 1 in terms of time to go from theta 1s to theta 1f. This starting and final positions are still same, but now I have to define a time trajectory for theta 1 and time trajectory for theta 2 to make sure that I move along this path alone. Okay, I don't kind of deviate from this path. Okay, so that's what is a tracking problem. Okay, so this is called a trajectory tracking kind of a problem, and this problem has then explicit time dependence because theta 2 desired is a function of time here. Okay, or theta 1 desired is function of time here. Okay, both are functions of time. Okay, and in the previous case, theta 1 desired was just a final value of like final value theta 1 f. Okay, and theta 2 desired was theta 2 f. I didn't have any like consideration for like what happens between like from 0 to or from initial position to the final position. Okay, so that is difference between the regulation problem and the tracking problem. Okay, the tracking problem will have a explicit time dependence. Regulation problem will not have explicit time dependence. Okay, so these are the steps you will typically follow, as I said earlier. Use for getting this theta desired trajectory, you use inverse kinematics of the manipulator. Okay, that inverse kinematics you will get from kinematic relationships, and again you will have to kind of use some control to do this motion along the path. Okay, so these two problems are there in the typically in the control domain, and we will see how we can now make use of the fundamentals from the control domain to get to these problems. Okay, I think we'll stop here for now.